detector response. Now, you have to actually choose the detector according to your sample, that which type of sample you are using, what is the nature of different analytes, what is the boiling point of different analytes present in that given sample. So for example, if you are using a flame ionization detector then it is stable at all temperature. Okay, similarly, if you are using thermal conductivity detector, then there are issues with the baseline with temperature. Similarly, if you have a mass spectrometer, that is, if your GC is attached with a mass spectrometer, then there are chances that if you increase the temperature, then ionization may increase, and if ionization increases, then fragmentation pattern will shift. Actually, there are number of, we have already seen while discussing the GCMS, that the cations will produce, and when they are directed towards the separation, then they will separate on the basis of M by Z ratio. So you have to be very cautious while choosing the detector for a given type of separation. Similarly, there are certain applications of temperature program. For example, temperature programming is very well suited with regard to the environmental samples, where you have to analyze certain volatile organic compounds, certain pesticides, certain PCBs, you can say, polychlorinated biphenyls. So it is very important, because they have a very vast difference in the boiling point of each component. So you have to use temperature programming. Similarly, in food industries, to detect certain aromatic compounds, to detect certain fatty acids, again temperature program is very important. It gives you very fine, very reproducible results. In pharmaceutical also, to check the presence of residual solvents or to check the impurities, because this chromogram, this GC technique is very sensitive, and you have detectors which can detect the impurity up to a level of 10 raised to the power minus 15 gram. We have seen while we were discussing the detectors. Similarly, in forensics, where you have to check certain drugs, certain performance drugs in case of athletes. So those small concentrations can very well and can easily be detected by the programmed GC. Similarly, we have seen that if you are going to analyze certain petrochemicals, which ranges from, in the early example, we have seen from 8 carbon to 30 carbon, you can very well get a well separated chronogram, where each component is defined by each well resolved peak. So it is very good. Even ASTM has also recommended to use a temperature programmed GC. Okay. So there are special cases also. For example, if you have a very volatile compound, then you need cryogenic cooling, or you have to start from a very low temperature, sometimes minus 10 or minus 20, because otherwise you can miss certain volatile compounds. For example, if you start your GC from 25, then you will miss all those which has a boiling point less than 25. So you have to start from minus 5, minus 10, depending upon the nature of the volatile components. Similarly, if you have very high boiling points, then you have to use programmed GC or a stepwise GC, or sometimes you can also use the GC in which the temperature rises exponentially with a very high ramp, and that can go up to 350 degrees centigrade. Similarly, you can use multi-ramp programs for a complex matrices. For example, if you have a mixture where 3 components are having narrow temperature difference, boiling temperature difference, and 2 are having a difference, so you can use, initially you can use an isothermal, then you can couple it with that programmed detector. So you can use multi-ramp programs. Similarly, for example, if you want to separate some corrosive substance, then you have to use some Teflon coating. So in each case, the moment you change the case, the condition will change, and the precautions which you have to take will also change. Similarly, if you are using an FID, then you have to look for that for controlling the explosive mixture. So every time the condition changes, the precaution changes. Another special case is the hydrocarbon mixture. For example, if you are running in an isothermal condition, then there are chances that you will get some unresolved peaks, because the moment your skeleton grows from more than 20 carbon, then there are chances that your isothermal column or your isothermal oven will miss all those peaks. So in that case, you have to use the programmed GC so that you can get a full resolution. For example, here you get full resolution in just 45 minutes. As I discussed earlier, now the ASTM, that is the American Society for Testing of Materials, are recommending to rely on the programmed GC. For example, in refinery quality control, it is always the programmed GC, not the isothermal GC. So isothermal GC is a traditional one, is avoided in such cases, is avoided. Okay, so depending upon the requirement, you have to look that how you are going to optimize your different conditions, how you have to optimize your column with regard to temperature, with regard to constant temperature, with regard to ramp, with regard to the retention time. So you have to look, you have to look for on a case-to-case basis. Another case, for example, if you want to separate certain essential oils which contains terpenes and some substituted terpenes, let us suppose sesquiterpene. So if you run a column, then of course this terpene will come initially and sesquiterpene, which is a derivative of terpene, will come late. And there are chances that if you do a isothermal GC, then these two, that is the terpene and the sesquiterpene, will co-elute. They will elute at the same time. That is, they do not have well separated peaks. That is, co-elution may occur. So in that case, you have to go for a programmed GC so that you can have a very effective separation of the two. So what you have to do, that you have to use the GC with temperature programming, and if your detector is a mass spectrometer, then you can do the fingerprinting. You can have a qualitative, you can actually, by coupling GC and MS, you get identification, you can do qualitative test, and of course the most important one is you can quantify. So you can do three important things, and of course, since you are doing mass, so you also get structural information. So you can see the beauty of using the GCMS. For example, in case of the natural products. Similarly, software interpretation. Nowadays, software is also become very important. For example, if you have a peak deconvolution, that is, the peaks are coming like this. That is, peaks are coming like this, for example. Now, you have to deconvolute it. That is, you have to separate these peaks. And you can see that baseline is missing. You can see that although these are overlapping peaks, you can see that these are component 1, component 2, and component 3. So you have to run certain computer program, and by running it, you can get like this. Now you can see a perfect baseline, and all the 3 components are well resolved, and the baseline is also corrected. So this is actually called as peak deconvolution. That is, you actually separated the overlapping peaks by using a certain computer program. Okay, so you can also do some automated search. You have a database, and you just, on the basis of TR value, you just search it from your database and you actually match it. We are going to study this when we discuss the coverts method. Okay, so you can do a library search. Similarly, now the modern software, the modern GC software is coming with all these tools where you have an inbuilt library in the GCMS, and the GCMS actually do certain permutations and combination, and it matches your peak height, and also the TR and other factors to its library, and it gives you proper identification of unknown compounds unknown compounds on the basis of their TR, on the basis of the height of the peak, on the basis of the width of the peak, and on the basis of different conditions. Okay, so this is actually you are using artificial intelligence to get a real-time picture of your chromatogram. So what are the key learning features? What are the important features? So for getting a good, you can say, interpretation of your chromatogram, you have to look for retention time. You have to look for peak area, shape, that your shape is Gaussian or not. You have substantial peak area or not. The retention time is different for every component or not. Or there are chances that if the two components are having the same retention time, then you can say that they are co-eluting. So you have to look that whether it is some impurity or it is something extraordinary coming out, because two components cannot have same TR. Similarly, you have to look for the baseline. You have to always have a very smooth baseline, a straight line like this. That is called as the ideal baseline. It does not have certain noise or anything like this. So it must be avoided. And of course, the resolution, that is RS, is always greater than 1.5. So you have to look your chromatogram in terms of the retention time, in terms of the peak area, in terms of the peak shape, in terms of the baseline, and of course in terms of the most important aspect, that is resolution. Okay, so you have to look all these features, and there are certain tools which are going to help you out. First of all is the temperature programming. That is, you can do temperature programming to get well resolved peaks. You can get the peak of the last component by just changing the temperature, by just changing the GC temperature, that whether you are using the isothermal GC or you are using a programmed GC. So temperature, or you can say programmed GC, gives you the tool to separate wide boiling point components. Okay. Similarly, optimization. You have to optimize your ramp rate, and you have to look for the initial temperature of your column, that at what temperature you have to start your column, and that start temperature is decided by the boiling point of the component of the least boiling point component. Okay, and you have to also adjust the carrier flow, because this is very important. If you increase the flow rate, then Cu will increase. Okay, so you have to look for the ramp rate, you have to choose the start temperature and also the stop temperature, and you have to look for the U, the carrier gas velocity. So multi-dimensional GC, that is GC into GC with temperature programming, is actually the future, or you can say it is actually the, you can say, silver lining, where we can couple one GC with another GC, where one GC has having certain detectors, certain columns, and the other GC has certain detectors and certain column, and you will get super specialized or highly, you can say, a highly separated components, even greater than that of 10 to the power 15 gram value. That is, more than this purity of your sample you can procure in the future by combining two GCs. Okay, so what is the essence of GC interpretation? So what is actually the summary of all this discussion? So qualitative analysis, that you have to identify. Qualitative analysis means that you have to identify on the basis of the nature, that how many different components are there, how many different components are present. Similarly, when you are sure that okay, 5 components are there, then you have, for example, if you have 5 components A, B, C, D and E, now you have to look at how much quantities of each component is there. Okay, it is, for example, 250 milligram, it is 85 milligram, it is 200 milligram, it is 700 milligram, and it is 400 milligram. So this is called the quantification, that you have quantified each of your component. And the dual nature of GC is that it gives you a qualitative as well as the quantitative ideas. Okay, so you can do dual things with this, and you have to always look about your column. You have to check the history, that what was the nature of the last sample run by that particular GC. Because if there may be some unretained species, then this unretained species will going to affect the whole resolution, will going to affect the whole separation process. So you have to look for the column history with regard to the different analytes which were resolved earlier, with regard to their boiling points, with regard to their polarity, that how much they have actually retained. There are chances that some of the earlier sample might have retained with the stationary phase on the basis of polarity. For example, if you were using a non-polar phase, for example, and there may be certain hydrocarbon, then there are chances that the early hydrocarbon may still be sticking with the stationary phase. And the moment you increase the temperature, that will come out. It will create a fuss in the whole separation process. Your whole separation process will be compromised. So you have to check the history in terms of the temperature, in terms of the binding, or you can say interaction, that is which type of interaction was there, which type of stationary phase you have chosen, which type of mobile phase you have chosen, and what was the temperature of your GC, what was the working temperature of your GC. So you have to check with regard to the retention time, and you have to compare with the standards. So comparison with the standards gives you an idea that you are working in the right direction, that you are actually having a good quantification and good you can say separation. So workflow, that how actually you started and what were the steps which you encountered while separating compounds from the GC. So initially it was a sample. You must have a sample in the vaporized state always, because this GC is good for the vaporized sample. This is the beauty of GC, and sometimes it becomes a drawback of GC, because you cannot analyze all the samples from GC. You can analyze only those samples which are in the vapor state or which can be vaporized. And we know that from our knowledge of chemistry that every substance cannot be vaporized. So if the substances cannot be vaporized, then it cannot be separated by GC. So initially you have to check the sample, you have to check the state of the sample. So your sample must be in the vaporized state. If it is not in the vaporized state, then you have to vaporize it before injection. So you have to vaporized. Your sample must be vaporized. Vaporized. Then you have to inject this sample. Now the injection is very important. That which type of injection port you are using, whether you are using the split injection, whether you are using the splitless injection, or whether you are using the on head column injection, that is called as cold on injection, depending upon the nature. For example, if you are using some thermally labile compounds, then you cannot do the splitless or split injection. Then you go for the head on or on cold injection. Similarly, if you are using some trace analysis, then you have to use the splitless one. So depending upon the nature, again the nature of the volatile sample, you have to select the injection. Similarly, then the separation occurs. That is actually occurs in the heart of the column, that is which contains the stationary phase and the mobile phase immobilized on it. For example, if it is GSC, then you have the adsorption, that is the principle will be adsorption of the solute. Now, but if you have GLC or GC, then it will be the partition of your components between the stationary phase and the mobile phase. Then comes the detection, that are called as the eyes of the GC. So you have to very cautiously select which type of detector you are using or which type of sample you are having. For example, if you have a carbon based sample, then you can go for FID, that is a flame ionization detector. But on the other hand, if you have some inorganic compound, then you cannot do it for FID, then you have to select for TCD. Similarly, if you have some chlorinated, for example, if you have some nitrogen, then you go for NPD. Similarly, if you have some phosphorus, then you have to do some thermionic detector. So depending, for example, if you have some ionizable gases, then you can go for photoionization detector, PID. So depending upon the nature of the sample given to you, the nature of the problem you have to choose the detector very intelligently. Then the detector gives you some data, and that data is actually interpreted in terms of the chromatogram. So at every stage, there are chances of errors. There may be chances that you cannot vaporize your sample perfectly. And if you are unable to vaporize your sample perfectly, then there are chances of, error. Or you have chosen the wrong injection port. For example, if you have overloaded your column, then your efficiency will be compromised. You do not get proper resolution. Or for example, if the interaction of the solute is too much, then adsorption also occurs and tailing will happen. Okay, so every time you have to select, there are chances of error on every step. For example, if you increase the temperature too much of the column, then your stationary will start coming with the eluent. That is, you can say bleeding will occur or drift may occur. Extra electrons are produced. So every time there are chances of error in each case. So you have to be very cautious. If you are going from one to another, you have to be very cautious. So initially you have to prepare a very good sample, very good vaporized sample. Then you have to have proper injection with regard to the nature of the sample. Then you have to selectively choose which type of column you are using, whether you are using closed column or you are using open tubular column, whether you will be using WCO2, COT, or you will be using the surface coated open tubular column, depending upon the nature. Whether you are using the stainless steel capillary column or you are using, for example, a fused silica column. Then if you are using the fused silica column, then whether you have done certain protections or not, whether you have coated it with polyamide coating or not. So you have to take care of, you have to be very cautious. You have to take care of each and every step. Otherwise, you will end up with error and you will be nowhere. You do not get the desired results. Similarly, choosing the proper detector. And then after that, interpretation. So every stage, there are chances of error and you have to be very cautious at every stage. Okay, so qualitative analysis in GC and the retention time as the identity marker. As I have already explained that it is the TR, that is the retention time, which is the main marker, and that can be measured directly from the chromatogram. Because you cannot measure other quantities. You can measure TR, retention time. If you have more than one component, you can have TR1, TR2, TR3 depending upon the number of components. Similarly, you have TM, that is called the retention time of the mobile phase alone or the carrier gas alone. Now, with respect to TR and TM, you measure the different retention times. Similarly, you have to measure the peak width, sometime half of that of each one. If you have more than one, then you can W1 of 2, that is for each component. So that is actually retention time is called as the most vital aspect of GC, and it is the identity marker. That is why it is called as identity marker. So this TR actually tells you about the evolution of the detector signal. Similarly, it is dependent on which type of column you are using. The temperature programmed, the carrier gas flow, these are all affected. So relative retention time versus standard reference standard actually improves the reproducibility. So if you know the standard, then you on checking it with your component, you can say that okay, this one is this compound and this one is this compound, on matching their TRs, their retention times, because TR is actually the identity marker. So that is the most vital you can say property of any GC or of any component. Now the retention index, Kovacs index. because there was actually a scientist whose name was Eric Kovat, who introduced this retention index concept. And the introduction of this concept was to get an idea, to get a comparative idea of a standard. And he has actually chosen a series of alkane to generate this Kovat index. And this Kovat index is generated by using alkanes, because alkanes, on increasing the number of carbon atoms, they have the increase in a very ordered manner. That is why he developed Kovat index on the basis of the alkanes. For example, if you think in terms of the N-butane has a Kovat index of 400, but for pentane it is 500. So the moment you increase one carbon atom, the increase is very measurable and very specific. That is why he standardized it on the basis of the alkanes. And the formula is here. For isothermal runs, the logarithm can be obtained and the numerical value can be calculated by this. Again, this is done so that we can compare it with the standard compound. Okay. So we actually prepared Kovat index for a number of compound, and the moment we run it for some unknown, we try to match that index with the already reported one, and then with the already reported one, that we call authentic samples. So we compare it with the authentic samples, and then on the basis of the comparison we say that okay, this compound is this and this component is this. Okay, so this is like this. The formula is written here, we are going to use it sometime. The analysis for recording the sensitivity, where actually organic carbons or organic compounds are involved, because all organic compounds have a carbon backbone, and FID is actually based on the combustion of the carbon, which produces a signal which is actually proportional to the ions produced. Similarly, we have TCT, which is again a universal detector. It is called universal detector because it can detect both organic as well as inorganic compound, and it is non-destructive. This is the beauty of this FID, of this TCT, because FID was destructive, because your sample was combusted in FID, but in TCT it was not. It was a non-destructive. Similarly, we have the electron capture detector. It was very good for detecting the halogenated compounds, for the nitro aromatics, and particularly for the polychlorinated biphenyl PCBs that are very harmful from environmental perspective. So ECTs are very good for monitoring the environment or for the environmental contaminants. Similarly, we have the mass. That was the best one, because it also gives you the structural information. Again, it also uses a similarity index pattern, because it also has a library, so you can always match your unknown compound, and then you can get an idea that okay, this is this and this is this. Okay, so the tip is that you have two orthogonal identities, that is the RT and the spectral match, that is the detection time and the spectral match. Okay, so peak purity and coelution. Now the peak must be, ideally your peak must be Gaussian in shape, and that tells you about the purity, because if you get a broad peak, then there are chances that it was actually this. There are chances that it is actually, if you get this peak experimentally if you get this peak, then there are chances that it has actually superimposed these two components, A and B. That is, A and B remains unresolved here. Remains unresolved. So if you get a shoulder like this, then this tells you about the coelution. So you have to use, now what you have to do, you have to use certain programs. You have to slow down the ramp rate, so that the moment you slow down the ramp rate, they will be separated. Again, you have to do certain deconvolution by using certain software. Again, you can combine two GCs, so you can get a very good resolution. So peak shape actually tells you about the column chemistry, because this actually part, this is called the fronting part. This part composed of those eluent molecules which have the strongest interaction with the mobile phase, and this part constitutes those eluting molecules which have the strong interaction with the stationary phase, and the middle path, that is middle one, is for the intermediate strength. Okay, so this fronting is because of the strong interaction with mobile phase, and this part has because of the strong interaction with stationary phase. So ideally your peak must be Gaussian like this, no fronting, no tailing. So you can see no fronting, no tailing. So the peak shape actually indicates the column chemistry, that which type of interaction is actually dominant. If you have a fronting, you have a long fronting, it means the dominant interaction is the mobile phase interaction with the solute molecule. If you have a long fronting, if you have a long tailing, then it implies a dominant interaction of the stationary phase with the solute molecules. Okay, so it is like this. Now, what are the applications of the qualitative GC? For example, you can check the fingerprinting in terms of the different constituents. For example, you can check vanillin, terpenes. Vanillin is the component. Vanillin is the compound which is found in every eatery. All the chocolates, all the biscuits contain vanillin. Similarly, this is very good to check the forensic identification of drugs. Nowadays, it is also used in certain postmortems to check that whether there is some drug poisoning or there is some abuse of some poison or not. So GC comes into play. Even nowadays, you can see people checking the traffic police. Actually, they have a certain you can say certain bands, and they just check the smoke, they check the breath, and they tell you that whether a person is alcoholic, have taken alcohol or not. So that is actually very important. Similarly, petrochemical isomer separation. You can do environmental monitoring by checking the volatile organic compounds, and as well as certain nitrous gases and certain sulfur dioxides and sulfur trioxides. So all these you can do by running GC. So with this, thank you very much for your patience hearing. We will be coming back with a new set of slides. Thank you.